All right. Welcome, everyone, to a series of 2 workshops that we're going to be running for the next 2 hours. The first is a ZK Battleship tutorial. So this is basically a live coding-ish exercise to get people on the board and comfortable with writing your first circuits in SIRCOM for ZK Snarks. We're going to build out a couple primitives for a simple battleship game and explain why ZK Snarks are interesting and useful here for on-chain games. The second workshop that we're going to be running in an hour is a collaboration between myself and Nalin, where we're going to be exploring techniques for procedural generation in on-chain games. So specifically implementing procedural generation algorithms in Solidity and inside ZK Snarks so that you can build rich and textured worlds. As just like a quick reminder of scheduling related things, currently there's also a Dark Forest talk going on downstairs by Ivan. And I believe that, oh, actually, does anyone know what the 5 to 6 workshop is downstairs? I don't quite remember, but everything is on DEF.CON.0xpark.org if you're curious. Okay, cool. So before we get into the coding part of this workshop, I want to give a little bit of a high-level overview about why ZK is useful in games and why we care about snarks in the context of crypto gaming broadly. So the first thing that I'm going to do just to motivate the use of ZK snarks here is I want to define 2 terms that are commonly used by people who think about games, and that is complete information games and incomplete information games. Oh, yeah. So complete information games are games like chess and checkers, where everyone knows the full state of the world. So in chess, I know where all your pieces are, you know where all my pieces are, there's no secrets. Whereas incomplete information games include games like poker or StarCraft, where there is some hidden state or information asymmetry between the different players. So for example, in poker, I know my cards, but I probably don't know the other cards of the other players in the game. So complete information games for a long time were the only kinds of games that we were able to build on blockchains because blockchains by design, in addition to a lot of decentralized systems, are these completely open and transparent data layers. So anyone can inspect publicly the state of a smart contract. We can't really bake in granular read permissions into a blockchain the same way that we can with a server. And as it turns out, pretty much all of the major multiplayer digital games that we have today have some component of incomplete information because incomplete information games oftentimes have much richer strategy spaces. So, when we look at blockchain games of kind of the last couple of years, we see things like CryptoKitties, where it's a simple trading card game where everybody knows who owns which kitty and what the properties of each kitty are. I kind of look at this as almost like, blockchain's like tic-tac-toe era of games. And I think that with these new primitives like ZK Snarks and some of the other things that we've seen today, we can go much further. So a key component of many games is this idea of information asymmetry. This often comes up in, for example, strategy games such as StarCraft, where there's a fog of war. I might not know where your base is or what you're producing, and vice versa. Similarly, in Dark Forest, you don't know exactly where all of the other players' bases and planets are. That's one of the core mechanics of the Dark Forest game. I have a screenshot from, I believe this is a screenshot from Eve here. For these extremely complex games, the fact that there's information asymmetry is almost just taken for granted. Information just becomes a first-class resource which can be traded just like with, resources or currencies or any other in-game items. Incomplete information allows us to see things like emergent social dynamics, or large-scale player coordination, or conditional coordination, or deception and lies and bribery, all these sorts of things that make the social aspect of a game rich and interesting. Finally, another thing I'll mention here is information asymmetry. Like, even though we've mentioned things like, fog of war or information as a first-class resource, a lot of times it's just something we take for granted. We don't even really think about it as a mechanic. So, for example, if I'm thinking about an RPG game or an MMORPG game such as RuneScape, there's sort of just this expectation that if I walk up to the RuneScape bank, I can't just see someone else's bank account. This isn't even really a mechanic so much as it is like, this is just water. It's just table stakes for us. And the fact that we can't do these things, at least with sort of the designs of early blockchain games, is a major limitation. So how do we use ZK snarks to hack incomplete information onto a blockchain? It seems like kind of a counterintuitive concept, because if we're working with this completely open and transparent data layer, but we want to store a private state, these things kind of seem fundamentally at odds. Well, it turns out that once zero-knowledge proofs for general computation are possible to make on-chain, there's sort of a general pattern space that we can explore for designing private information mechanics. So in the diagram here, on the left side, I have this box labeled player, and that's basically like the player's state of knowledge about the world. And on the right side, I've got network, which is basically, you can imagine that as the data that is being held in smart contract or on the blockchain or being gossiped on the peer-to-peer network for any kind of decentralized architecture. And we're going to say that the player is going to start with some private state S1. This is some secret information, maybe their cards, or their inventory, or the location of their base. And this is known only to the player and not to the network. Now, we want this state to be a part of the global game state, so the player is going to have to transmit something to the network. And what the player is going to do is, the common pattern is that the player is going to generate a commitment. For example, they're going to run a hash function on the private state, and they are going to publish that up to the network. So here you can see I've got this commitment C1 that is stored in a smart contract or wherever else is public facing. Now, the player needs to prove that they're not cheating. The whole sort of difficult problem here is, like, if the player can commit any data, maybe the player is just going to commit like that they have 2 aces every single time if we're playing a card game with hands of 2 cards. So we're also going to require that the player publishes zero-knowledge proof that proves that this commitment C1 corresponds to a valid private state S1, which is indeed a valid starting configuration for their private state. So this is basically something that we can encode in a ZK snark, and we're actually going to be doing just that today. Now, when this player wants to make a state transition, let's say they want to go from S1 to S2. That might mean drawing a card, moving a piece, sending some units over yonder. What they're going to do is they're going to end up in this new state S2, and they're going to publish, similarly, a commitment to S2. So, we might take a hash function and execute that on S2, and we're going to get a commitment C2. And just like we had to prove the original commitment corresponded to a valid private state, we're also going to have to prove, in this case, that there is a valid state transition that was executed properly between S1 and S2, which are the private states underlying what the network sees, C1 and C2. So by validating this zero-knowledge proof over here, we're essentially able to prove to the network statements kind of the form like, I'm moving my secret knight from secret location A to secret location B. I'm not going to tell you exactly where A and B are, but here's a zero-knowledge proof that can convince you that there's an L shape in between A and B. Okay, so with preliminaries out of the way, let's talk about ZK Battleship. So can I get a show of hands? How many people here are familiar with the game Battleship? Okay, cool. So that's almost everyone. Just to kind of, for those who aren't familiar, it's a really simple game concept. The idea is, each of us has a secret 10 by 10 grid on which we're going to place a number of ships. So in a simplified version, imagine that basically means picking like 5 points on the my private 10 by 10 grid. And you might also pick 5 points on your private 10 by 10 grid. Afterwards, we simply go turn by turn, and each of us will guess a coordinate, i.e. like launch a missile at some coordinate x, y, and it's up to the other player to tell the person whose turn it is whether or not that attack landed on a ship. And the goal is you go back and forth a bunch of times, and eventually, you're trying to sink all of your opponent's ships by hitting, i.e. like all 5 of their squares. Usually in like the traditional Battleship game, ships are actually like contiguous rectangles. So you're placing like a 1 by 5 rectangle on the board and a 1 by 4 rectangle, and then 2 1 by 3 rectangles and a 1 by 2 rectangle, and you're trying to wipe out all of the other opposing players' ships. But in our simplified version for now, we're just going to explore what happens when players have 5 individual points that each player is trying to guess the other player's configuration. So, first off, suppose that I am trying to build a Battleship game on the blockchain. Can someone And let's say that we try to do it as follows. The sort of naive way is that first you make a guess, and then I just respond to you yes or no, did that hit? And then like I make a guess, and you respond yes or no, did that hit? Can anyone see any issues with this game, with this version of the game? Yeah. Right, exactly. So, the thing that we might try to do is initially we set up the game by having both players, post 5 coordinates onto the chain, but maybe, we'll put them in smart contracts, and then we'll have each player guess, and the smart contract is going to check whether or not a guess is corresponding to one of the 5 locations that a player has, previously uploaded during the setup phase. This doesn't work because even if you hide the location of those ships from the UI, blockchain data is publicly accessible, and anything that you build on the blockchain is client agnostic. So you can just go to EtherScan, check the transaction history, inspect the smart contract state, and determine where the ships were placed. Okay, so what if we try to kind of preempt this? We say, you know what? You're not going to upload the ships in the first place, but you have to respond to each query that your opponent makes with whether or not that ship or that guess that they made hit one of your ships. What's the problem in this case? Yeah, exactly. So the problem in this case is that players can just lie. Even if you pick some 5 ships at the beginning, maybe this is a game with some money on the line. This is like the smart contract Battleship World Championships, and there's 100 ETH on the line. What are the incentives here for someone to basically say, oh, you guessed 1,3? Oh, actually, I didn't have a ship there the whole time. We see that there's kind of this like tension here between keeping players honest and ensuring that it's keeping players honest while also making it so that way players can't see each other's private data. And this is just like another example of this same kind of problem that we're seeing here and exactly what we're going to try to solve with ZK Snarks. So yeah, the question is, how can we play Battleship without a referee while preventing cheating? Before we talk about how to do this with ZK Snarks, I want to mention another class of solutions, which many of you may have heard of, called commit reveal. So the idea behind commit reveal is that initially players are going to commit to their private state. They're going to play out the game, and it's going to kind of be honor system for responding to challenges on the commitments. And at the very end, players are going to have to reveal their whole transaction log and their initial underlying private state. Because the player has committed to things ahead of time, they can't change their private state or configuration on the fly during the game. Like, you can't move one of your battleships while you are, in the middle of a game in response to a query. So that's what commit reveal enforces. And commit reveal is a very powerful tool, and it's used in a lot of different systems. However, it does have a number of limitations. While it does allow you to introduce incomplete information in certain limited settings, there are a lot of cases which commit reveal can't cover, and also a lot of disadvantages, both on the mechanical side and the UX side of the commit reveal strategy. So first off, commit reveal often requires a lot of back and forths. So, we might need to post a commitment and then reveal it after the end of the first round, and then another commitment and another reveal after the end of the second round, and so on and so forth. This can get very difficult, especially if you're dealing with on-chain transactions. Perhaps some of you have tried doing things like claiming a token mint or something like that that involves a commit reveal scheme. If you're on some blockchain network with high gas fees, this can be very inconvenient, and oftentimes the second step might fail if certain preconditions are not met for the first. Another thing is verifying integrity of a long chain of commitments and private state transitions is bad. This can be very expensive, and it can kind of grow in proportion to the length of the game. So, for example, on Dark Forest, let's say Dark Forest rounds were commit reveal, we're using commit reveal. Players during Dark Forest in total make tens or even hundreds of thousands of moves, and it would simply just be infeasible to sort of reveal the pre-image and do all of the checking on all of the game state for an entire round. And the last thing, and this might be the most sort of fundamentally problematic thing for a lot of games, is that commit reveal only works for eventually complete information games, i.e. games where everybody is fine if their entire private state and action log is revealed by the end of the game. So for persistent games where there's sort of an ongoing living universe, or for games where revealing your sort of intermediate steps might reveal inadvertently something about your larger strategy that you don't want to show, you don't want to be doing commit reveal kind of schemes. So yeah, this is where ZK snarks come in. ZK snarks essentially allow you to make those sort of one-shot proofs of the validity of initial state as well as state transition. And today we're going to be coding up some simple ZK snarks for a very simplified version of ZK Battleship. So the first thing that I'm going to ask everyone to do is to clone the gubsheep/ZK Battleship workshop repo if you want to follow along. And we're basically going to just be like going through this repo and using a couple of different ZK development tools to build out our simple version of Battleship. So you can, let's see, if you just go to this repo, the other thing while people are doing this installation, so basically you'll need node 16 or higher and you'll need yarn. You can clone this repo and then after that check out workshop-start. So this is basically like the starting point for today's workshop. And then you're going to want to run yarn at the root of the project. And that will install all the dependencies. So while people are doing that, and feel free to also interrupt me and raise your hand if you have any questions, I also just want to make a quick sort of plug for where this repo comes from if you want to continue playing around with snarks after the workshop. This repo is a fork of this very simple starter kit that we have for basically digging around with circuits, circom-starter. Circom-starter relies on some tools that a few folks in our community maintain, including, well, Circom itself, the Circom programming language, and hardhat-circom, which is a set of which is a plugin on the Hardhat task runner for those of you who are familiar with the Ethereum development ecosystem. Can you raise your hand if you have successfully completed the installation steps, and then we'll proceed after that. For those of you who are wanting to follow along. We'll give this like a minute or two. Yeah, question. Oh, yes. The question is this being recorded? I believe the answer is yes, and this will be posted after the conference. The other thing that you can do if you are interested in going through these sorts of materials, by the way, is we have a site, learn.0xpark.org, with recordings from our applied ZK learning group, which goes into much more depth than we're going to be going into today. Yeah. Show of hands if you've managed to complete the installation successfully. Okay, cool. All right, so a handful of people have gotten through it successfully. We'll move on to the next steps. And if you are having trouble again, feel free to raise your hand and we can try taking a quick question or two. If not, though, I'll get into the goals of basically like specifying what are we trying to do today. So our goal is to place 3 1-by-1 ships on an n-by-n board. Today, just for the sake of simplicity, that board is going to be 3 by 3, but we'll see it's pretty easy to extend this to arbitrary sizes. We're going to want to commit to our ship placement, and in doing so, prove that we've placed exactly 3 ships, no more, no less. So you can't cheat by putting 0 ships down, and then just like responding to any query with like, oh yeah, you didn't hit my ship. And that's, just to go back to this diagram, that's this first arrow, the pre-commitment, that shows that we have a valid initial state. And then what we're going to do is we're going to be able to make proofs that answer queries of the form, does your board have a ship at X, Y? To string this together into a full Battleship DApp, there's a little more work that you have to do, or whether you want to do it on a server or some peer-to-peer architecture. But for now, we're just going to focus on the snark part today. And hopefully you can see that like if you can make 0 knowledge proofs of these 2 things, that's basically sufficient as the engine for powering what a decentralized Battleship game would look like. So we would basically like each initially commit to some ship placement and then go back and forth on making queries and responding with proofs. So let's dig into these first two bullet points and specify a little bit more precisely what we mean. So what we're going to do is we're going to compute and commit to a board ID, which is going to be a commitment to the placement of all of the ships. So a zero-knowledge proof basically will demonstrate that for a given board ID, which is going to look basically like a 32-byte integer, for a given board ID, I know some configuration of ships on this n by n board, such that when this configuration is hashed, and we'll get into exactly how we're going to do that hashing and stuff, it results in this particular board ID. So before I go any further, can anyone see any issues with this kind of outline as I've sketched it, in particular for small boards, let's say like 3 by 3? Yep. Can you repeat that? Right, yeah, so one of the issues here is that you can brute force which ship configuration your opponent has committed to. So as an example, if I'm using a 3 by 3 board, there are only 9 choose 3 possible arrangements of ships, which is probably something like, somewhere in the range of a couple hundred or maybe a couple dozen ship configurations. So what a resourceful player could do prior to starting the game is they could go ahead and just compute the hashes of every possible configuration in a rainbow table attack. And when I publish my ship configuration up to the network, they would simply be able to look that up in their lookup table and say, oh, this is Gubsheep's configuration. I know exactly where his ships are. So does anyone have a suggestion as to a solution for this, what is called a rainbow table attack? Yeah, so the thing that is a common technique here is we will choose to salt the hash, which essentially makes it such that an attacker, in order to brute force the possible ship configurations, would have to search over a much wider space. I'm going to add basically a private salt, which is like sort of a board password, is one way that you can think about it. And the commitment that I make is also going to be a hash of my board configuration along with the salt. So I need to know both my board configuration and the salt to make proofs about the underlying state of my board commitment. And now, in order to determine my board configuration by brute force, what an attacker would have to do is they would not only have to iterate over all possible configurations, but for each configuration they would have to iterate over all possible salts. And if you take the salt space to be something like 256-bit integers, then the attacker's sort of out of luck. Yeah, and I also want to maybe more precisely define what these inputs and outputs look like. So what I'm going to do here is I'm going to want to be making proofs about this two-dimensional array called has ships. That's a 3 by 3 array, each of whose values is either 0 or 1, so 1 if there's a ship, 0 if there's not, as well as this 10th value salt, which can basically just be like it's any free integer. What I'm going to publicly compute is I'm going to basically take some unique serialization of has ships. So in this case, we can sort of interpret has ships as a bit string and then hash that bit string, and each bit string will uniquely refer to a single board. And I'm also going to hash that with the salt that we've privately chosen. This acronym-looking thing over here, MIMSI, is what is called a snark-friendly hash function. So when we're deciding what to use to make this commit, we have a variety of choices. For example, you could use the SHA-256 hash function or a number of the other standard and very popular hash functions. It turns out that for reasons that we'll get into in a bit, these functions are very snark unfriendly because snarks can naturally make proofs faster on certain kinds of mathematical objects but not others. And bits are a thing that is very hard for snarks to make proofs about. So to sort of improve the performance of these kinds of schemes that require snark-friendly commitments, we have invented snark-friendly hash functions such as MIMSI and Poseidon, which basically take advantage of kind of the natural structure of snark math. Okay, so there's actually a couple more things that we want to prove. I mentioned one of them. One thing that we need to prove is that has ships is an array of all zeros and ones. given our game goals, can anyone tell me what other statement I want to be proving in my zero-knowledge proof about the initial configuration? That there's free ones. Right. So we also need to prove, in addition to has ships is all zeros and ones, that the sum of all the values in has ships is equal to 3. And that will tell us that we've placed exactly 3 ships. So this kind of exercise that we've gone through, defining the inputs and the outputs, being very precise about what's being computed and what's being proven, is, this is kind of a taste of what snark/circuit engineering often feels like. You'll have to think through both the snark in the context of the larger protocol, as well as breaking down into a mathematical description of exactly what the snark is proving. So for much more complex circuits, these things can sort of grow substantially in complexity, and if you're interested in that kind of stuff, we have learning resources for going deeper down this rabbit hole as well. But we'll start with this simple toy example. Oh, actually, one more thing I'm going to mention here is that for our use case here, commit reveal is actually not too bad. The sort of weaknesses that we mentioned still do apply, but presumably if you're picking your ships randomly, then things like revealing the location of all of them at the very end is not too bad. So this is largely for demonstration purposes, but you can imagine basically extensions on top of this game that really get gnarly unless you're using snarks. Cool. So what we're going to be writing our circuits in is the CIRCOM programming language, which is maintained by IDEN3, a team which is also implementing the Hermes rollup. And what CIRCOM allows you to do is it allows you to define and write ZK circuits, which are kind of like programs in snark land. They are the blocks of computation that we're proving were executed properly and for which constraints are satisfied on. So there's 2 things that you can do in this computational model. It's a little bit different from the typical computational model, and we're not going to go into all the subtleties here. But at a high level, you can think about this as you can prove that a computation was performed correctly. So let's say you evaluate a polynomial, you get some number at the end, you can prove that that polynomial was indeed evaluated correctly on your input. And you can also prove various constraints on intermediate values. And this is sort of basically inserting assert statements inside of your ZK snark code. And then if you insert these assert statements, then what's eventually going to come out the other end is a proof that all of those assertions held. The last thing that's kind of interesting about snarks is that, the technology is still very immature, and we are programming at kind of the very, a very low-level representation of programs. In particular, the way that snark protocols often work is that, snark protocols will generate proofs on computations expressed as arithmetic circuits. And what this means, sort of in layperson terms, is that only plus and times are allowed. So you're only allowed to do computations and prove constraints that use plus and times. For the more mathematically inclined folks in the room, the other kind of thing that you have to keep in mind here is that all of your integers, all the numbers involved in these proofs, are actually field elements modulo a really big prime. So for example, if you add 2 really big field elements, you can wrap around, or if you multiply 2 big field elements, division has a slightly different meaning, but for the purposes of this, we can basically think about this as only plus and times are allowed. And we're going to be using today's ZK REPL, which is a collaborative in-browser CIRCOM IDE that allows you to do a bunch of really neat things. So before we go into the repo, we're going to go to zkrepl.dev. And here you can see this is actually a project built out by one of the folks from our most recent ZK Learning group. This is a cool little tool that allows you to build circuits and prototype things and save them and share them collaboratively. So it's got an example circuit when you load up the web page to start with, and you can sort of see that this CIRCOM programs or CIRCOM circuits roughly take the shape of things that look kind of like programs. So you've got these input signals, you've got output signals, you have the ability to declare that this output signal should be this certain function of the input signals. That function only uses plus and times. And then we also have this thing over here, this idea of components, which is essentially these are reusable, sort of kind of analogous to functions that you can import in from other circuit libraries and use in your own circuits. So Poseidon is a hash function, and we're going to use the mimc hash function, which is a different snark-friendly hash function. But you can see an example here of basically like computing a hash of the two inputs. One of the nice things about zk-REPL is that you can basically like test out running this circuit and generating a proof on different inputs. So if I just press Shift-Enter here, then I'm going to generate like, I'm going to log some stuff. I'm going to like generate a proof and verify it on these particular inputs. I can try like a different set of inputs, and I get a different set of log outputs, and then I can download various artifacts that are generated during the compilation process. Yep. Oh yeah, I can do this. Yeah. Cool. So let's try to write the circuit for the Battleship initial configuration. So what I'm going to do here is I am going to, and also another thing that you can do is you can check out the completed circuits and a slightly cleaner version of the circuit that uses some more advanced language features in the slides, which I will make available somehow if it is possible after the end of this. And yeah, you can check also the reference implementation in the Battleship workshop repo if you're curious. Okay, so let's go ahead and write the board ID circuit. Again, this is a circuit that commits us to a ship placement. There's going to be two inputs. The first input is an array that is 3 by 3 of has ships. The second input is a salt. There's a computed output, which we're going to call the board ID. And in addition to proving that the board ID is indeed equal to mimc of board to bits of the ships array, comma salt, we're also going to add in assertions that exactly 3 ships were placed, and that each of the values in has ships is either 0 or 1. And all of this is going to be done using only plus and times. So we're going to do a couple little tricks to make that work. Okay, so let's go into our zk-REPL. Let's call this board ID. And we're just going to go ahead and define our inputs and outputs. So the first one was has ships, and that's a 3 by 3 array. And the second was salt. And our output, we're just going to call board ID. And we're going to delete this and basically like start putting together this circuit. Okay, so let's start with these two assertions that we are wanting to make about the ship configuration. Namely that each of the values in has ships is either 0 or 1, and in total there's only 3 ships. So let's start with the first one. Normally, if I'm in a regular programming language and I want to prove that a number is either A or B, there's usually a lot of really easy ways to do that. I can write a function that compares the number in question to A and then the number in question to B, and if at least one of those is true, then my function can return true. In this case, however, we only have access to plus and times. Like, we're really just working with some like very basic tools here. Can anyone basically, so I mean, I guess just to like, explain a little bit more what that means, we can make assertions about statements like A times B equals C, or A plus C equals D, or like A times B plus C minus F equals Q. That's the sort of thing that we can make assertions about. We can't make assertions like, A is B or C directly. So can anyone, does anyone have an idea of how I can use just plus and times to essentially constrain each element of has ships, let's say we're working on 0, 0 right now, to be either 0 or 1? What's an equation using only plus and times that if this equation is true, then has ships is either 0 or 1? Yeah, in the back. Right, so exactly. So this is a clever trick where basically what we're going to do is we're going to say that I'm going to rephrase your equation slightly, and I'm going to write it as has ships times has ships minus 1 is constrained to equal 0. So we can see from this equation that if has ships is 0, this equation is true because 0 times negative 1 is 0. And if has ships is 1, then we have 1 times 0 is 0, so that's also true. And if has ships 0, 0 takes any other value, like let's say it takes the value 5. Let's say it takes the value 5. Then what the left-hand side of this expression is going to evaluate to is going to be 5 times 4, which is not 20. So we can see that if this equation is proven to be satisfied, then we have constrained the value of has ships to be either 0 or 1. And this kind of reasoning is sort of going to lie at the heart of what ZK circuit programming looks like. A lot of times you're going to have to make these sort of indirect kind of statements about the things that you're trying to prove because you can't express these things in normal programming logic, though higher order tools are currently in development. Okay, so I'm just going to do the dumb thing here and basically copy paste this 9 times. And what this is doing is it will demonstrate, or it's going to prove that the entire board is indeed composed of zeros and ones. Okay, so the next thing that we're going to want to do is we're going to want to prove that exactly 3 ships were placed. Can anyone tell me how I can go about doing this? Sorry, can you explain? So the suggestion was keep a counter. Can you explain what you mean by keep a counter? Yeah, so the thing that we would like to be able to do if we were in kind of a regular programming language is we might want to write something like, var count equals 0 for var I equals 0, I less than, let's do this. Oops. So we'd like to be able to do something like this. While it's going to turn out that circom syntax does allow this, what's actually happening under the hood is that this sequence of expressions is getting converted into something that, again, only uses plus and times. So this is syntactic sugar that should not be interpreted really as how for loops usually work as we're used to them. And the challenge actually that I'm going to issue to everyone is without this sort of advanced syntax, because the advanced syntax is not going to work, what does it look like to only use plus and times? Yeah, is that also what you were going to say?
Here, actually. I meant to sum all the elements, and the sum should be 3.
Yeah, so what we're just going to do is we just have to unroll the whole thing. So I'm going to say that the following constraint is satisfied, 3 equals has ships 0, 0 plus, and then we're just going to, and you can sort of imagine that with syntactic sugar and macros and stuff like this, we can make this process a little easier, and that's really what's going on under the hood. But just to sort of illustrate that everything going on at the lowest level is plus and times, I'm going to write this out in terms of simply plus and times. Okay, so now we have proved that all values are either 0 or 1. Also, there's exactly 3 ships. So our last task here is to compute the board ID from has ships and the salt. And one thing that we could do is we could hash each of the 9 numbers sequentially, and then also hash together with that the salt. And this would essentially amount to hashing an array of 10 numbers together to generate a unique commitment. The reason that we're not going to do this is because in snarks, if you want to hash more things together, that's more expensive. And snarks in general are very oftentimes bottlenecked on computation. So snarks today are very slow and quite expensive. And in general, what we want to do, a big job of the circuit engineer, is to build snarks in such a way that they use a minimum of constraints. So what instead I'm going to do is we're going to define a basically intermediate signal that is a serialization of this array that's one-to-one. And we're going to hash that serialization instead. So I'm going to declare this signal board bit string. And what I'm going to do is I'm going to set it to basically be equal to the value of the bit string whose digit places are all the values of has ships. So I'm going to write board bit string, and I'm going to compute this as, and here I'll just copy over from the reference implementation so I don't have to type this out again. Board bit string is going to have in its 2 to the 0 place has ship 0, 0. In its 2 to the 1 place has ship 0, 1, et cetera, et cetera. And hopefully you can see that board bit string is indeed a unique representation of of this array. I'm going to call this has ship. Okay, and then finally what we're going to do is we're going to plug board bit string as well as salt to get board ID. And in order to do this, I'm going to pull in a component because I don't want to write an entire hash function myself. I'm going to write component hasher equals mimc sponge. And then what these values basically mean is this 220 is a security parameter for the hash function that you don't need to worry about. This number 2 means that there's 2 inputs to the hash function, and this number 1 means that there's 1 output to the hash function. And I'm also going to have to import mimcsponge.sircom. One thing that you can also do is you can look up the actual implementation of these like hash functions and stuff in circomlib. This is basically like the library from which we are importing. And you can see that mimcsponge basically like has all this logic, and if you look down at like the very lowest level, you'll find that everything ultimately is just plus and times. So this is a hash function implemented entirely with just plus and times. So I've got hasher. Let's look at the inputs. It looks like I need to plug in my 2 inputs to this array hasher.ins. So I'm going to do board bit string here as my first input and salt as my second input. And it also requires a key, which you don't have to worry about for now. This is just like a thing in the mimc hash function. And then what we're going to do is we're going to set board ID to be computed and constrained as the output of hasher. So I believe that this is what outs looks like. Okay. Cool. And let me just look at my reference implementation and copy a sample input here. Okay. So now this is our circuit. And you can see that it's basically doing 3 things. The first is it's checking that the board that I have pre-committed to is indeed all 0s and 1s. The second thing that it's proving is that there's exactly 3 ships. There's 3 1s on the board. And the third thing that it's doing is it is computing a unique identifier of the board given the salt and the configuration. That is hard to reverse engineer the original configuration from. Yes, question?
Sorry, I didn't understand why k is supposed to be 0, and I also didn't understand the input parameters for the hashing function.
Cool. Yeah, so the first question is why is k 0 for this hasher? Basically, like, this is sort of like at a lower level of abstraction that we need to be aware about for this exercise, but k is basically a parameter that you can feed into the mimc hash function that kind of in its own way acts sort of like a salt. According to specification for like the mimc hash function, k should be set to 0. So here we just set k to 0. And the second question was about, is the question about like the syntax of these inputs?
No, maybe I missed it, you said it already, but the input for mimc sponge is 220.
Oh. Yeah. So these are, you shouldn't really think about these as inputs, but rather these are like parameters for this like sub-circuit that we're inserting in. So in particular, like hash functions can have multiple inputs and multiple outputs. So we're going to basically ask for the hash function, the version of mimc that has 2 inputs and 1 output. Because what we're trying to do is we're trying to hash this like serialized version of has ship with salt. This middle parameter, 220, is a security parameter. That's basically just like approximately speaking, like a measurement of like how many bits of security we believe this version of MIMC has. I can make it smaller if I want less security, but also want the snark to be more efficient. I can make it larger if I want more security, though that will increase the amount of total constraints in the snark. So the question is, when I say parameters when referring to these values inside the parentheses, does that mean that we can't put signals inside of here? Correct, yeah, so these are different from inputs. Basically, this is saying like initialize the version of MIMC sponge with 220 rounds of security, 2 inputs and 1 output. You can kind of think of this maybe as like a higher order function-ish that returns you a function that takes some inputs and outputs. This analogy is like not exactly perfect, but it's like conceptually sort of what's going on. Does that answer the question? Yeah, one more question? Sorry, can you repeat that? Yeah, that's correct. So one thing that we could do is instead of having just 2 inputs, I can make it so I have like 10 inputs, and then I'm doing like, has ship 0, 0, and has ship 0, 1, and et cetera, et cetera. The reason that we don't do that here, though that is also totally valid, is that hashing 10 inputs is more expensive than hashing 2 inputs. And again, with snarks, like snarks are super slow. This program obviously is like extremely trivial to compute for like a normal computational environment. Inside of a snark, we're already getting into the territory of like a couple like tens or hundreds of milliseconds to generate a proof just for some function so simple as this. So that's why we do this like one-to-one serialization, because it allows us to reduce the number of things in the hash function. And this is the kind of optimization that also is a big part of engineering with snarks. Any other questions? Cool. So this is our basically completed circuit. If you'd like, you can press, again, Shift-Enter to run the circuit and see, you get a unique board ID. I can test out, like, well, what if I, like, place my ships in something of a different configuration and use, like, a different salt? Then I'm going to get a different board ID. And along with this board ID, you can basically generate an accompanying proof that proves that I know some board configuration and salt that is valid according to the rules of the game and corresponds to the board ID. Yeah, question? Yes, so let's look at what happens if we do 2 ships. What you're going to see is assert failed. So this is basically saying like this constraint is not satisfied. A valid proof will not be able to be generated here. So yeah, that's basically a good test. You want to make sure that your circuits are proving exactly what you want to prove, no more, no less. And there's various like testing tools and stuff for these kinds of things. All right, so real quick, we're not going to go over exactly this, but SIRCOM has a number of what you can basically think of as like syntactic sugar kinds of features that allow you to do things that look like for loops. These are not like real like expressive for loops in the same way that you can have like conditions in normal programming, but what these eventually amount to is like at compile time they're sort of like unrolled into like this statement times like I times j times. But this is the sort of thing that like allows you to like make your circuits cleaner. So, all right, now that we've built our first circuit, let's hook it into the rest of our app. So the first thing that we're going to do is we're going to go into our local development environment, and we're going to fill in the board ID circuit with the circuit that we've just written. So if you go back to your ZK REPL, there's a bunch of other stuff sort of like outside the circuit. Don't worry about that. Just copy in the body of the circuit into this guy template board ID. And then what we're going to do is we are using, again, a ZK dev tool called hardhat-sircom. And what hardhat-sircom allows us to do is it allows us to run this command sircom::dev. And what this will do is it will compile our circuits and produce basically like the protocol parameters necessary to generate and verify snark proofs for this particular function. So if you run yarn circom dev, what you can see is that a bunch of math is happening. There's a lot of numbers. Cool. And then let's actually look at the files that were generated and just quickly mention what some of these are doing. So what's happened here is that we've generated, the important thing is this board id.zkey file. And this is basically like a set of cryptographic parameters that allows anyone to generate a zero-knowledge proof and for anyone to verify a zero-knowledge proof of like basically this function, this computation having been performed correctly. So this code has turned into a set of basically like, cryptographic numbers. And looking at those cryptographic numbers tells me how to generate a zero-knowledge proof if I'm running a function. And another set of numbers in this parameter set allows me to, like, given a proof, verify that that proof is valid. Okay, so now let's take a look at our application. So we've just compiled our circuits. And what we're going to do is we're going to run yarn client start to just start a local Battleship client that we can play around with. So here's just like our simple front end that allows us to sort of look at this demo. I have this grid of 3 by 3 squares, and I can just like select some 3 squares, and I can, pick a salt. And you can see here that like the board ID is generated on the fly. And one thing we can actually do to check that is, let's actually do this board and this salt and verify that I'm getting the same output in both my like test front end as well as my ZK REPL circuit. And yeah, as you can see here, we have board ID 1335, blah, 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 1335, blah, blah, blah. And someone just seeing the board ID would not be able to reverse engineer the board configuration here. So what I'm going to do is I'm also going to go to this subpage, verify board ID. And you can see that if I plug in a board ID, so let's say like this tab is player 1, this tab is player 2. Player 1 is currently doing their setup. They set up their ships, they set up their salt, and they press generate board ID proof. They're going to end up with these basically like this is a set of elliptic curve points. They're going to give that to player 2 along with their board ID, and that board ID is a commitment to not moving their ships around. So player 2 looks at that board ID, pastes in the proof, presses verify, and gets the result that this is indeed a valid proof. And just to check, we can also just like mess around and make a bad board ID, and you can see that verify state has failed here. So you can play around with this demo a little more. The other thing that we have here is basically like the proof generation for responding to a query on x, y. So let's say that someone fires at 2, 2. We would say that that's a miss. We have another ZK snark that you can take a look at in hit.circom. That's basically going to prove that whether or not you hit a ship or not for a given configuration of ships and a given query. And if you go to verify shot hit, then you can plug in a board ID, a row, a column, whether or not your opponent is claiming that the shot hit one of their ships, and then a corresponding proof of the validity of that claim. And if you generate a proof here, you can paste it into here. Let's just do that right now. Board ID, row and column are both 2. Player 1 would be claiming to player 2 that this did not hit, so I'm going to put a 0 here. And then to sort of demonstrate all of that to player 2, player 1 would paste in this proof, and you can see that verify state is verified. And if player 1 tries to lie and says that, like, actually you did hit a ship, even though there wasn't a ship here corresponding to this hash commitment, then the verification would fail. Question? Sorry, can you repeat that again?
So if I'm here to your player one, I have your secret proof to verify. Can't I just ask the proof without asking you each time I want to pick a game?
Oh, I see. So yeah, the question is, once I have sent a proof over from player 1 to player 2, does player 2 need to continue having repeated interaction with player 1 to make further queries? Is that right?
Well, yes, but if that implies I can just check where the ships are and then one shot over ship.
Right, right, and that would imply that basically like I can just like ask all the possible queries and see which ones would hit and would not. That's a good question. The thing that the proof is doing here is this is a proof specific to the query. This is not a proof about the global state. This proof would not work if I entered in like 1 and 2 or like 0 and 0 or something like that. So the proof is tied to the specific inputs that the prover is making a claim on. Does that answer the question? Cool. Yeah, so other than that, you can feel free to basically like play around with this repository if you'd like, and with this demo web page. You can see we've sort of set up this like very minimal end-to-end demonstration of how you would generate snarks, snark proofs in JavaScript and verify them as well. And you can also look in the ident3/snarkjs repo for a tutorial on this stuff, or learn.0xpark. We also have a bunch of open source repos with our like various prototype snarks and libraries that we use in more experimental projects. But yeah, that's all for this workshop. Any questions? Yes?
Just to prove that I understood correctly, so the way that I would play this game is that I am player 1, you're player 2. I tell you that I want to try to hit position 1, 1, for instance, and then you would generate the proof that it wasn't hit, and then I would be able to verify it. I cannot myself try to hit 1, 1 and check the proof.
Yeah, that's correct. So the question was basically just to like reiterate the conceptual model of what's going on here and how this game is played with these snarks. And indeed it is the case that like when player 2 wants to take a shot, what they're going to do is they have to ask player 1 to send them a proof, a response of whether or not that shot hit, that's a claim, and then a zero-knowledge proof of that claim. So again, yeah, if player 2 could just query themselves, then they would be able to just try everything and determine the location of the ships. Question?
So the solution must be implemented by some building up system, detect some the player just quick responding, quick reading the proofs.
If I understand correctly, the question here is, so this also must involve a system for verifying that each player is responding in a timely fashion. Is that the question? Oh yeah. So yeah, for example, like you could imagine a version of this, and we have some implementations, you know, as demonstration where you know, this game is played on a blockchain and you can time out the other player if they have not responded with a transaction claiming a response within a certain amount of time. Yeah, so ZK cannot, you know, force someone to respond. However, like ZK is less useful for things that require like heavy like state or time context, though there are some hacks that you can do. However, ZK is very valuable for being able to basically make programs and arbitrary, you know, sort of claims on the execution of them. Yeah, one more question?
We hear a lot of examples of ZK proof proving that you own at least that many tokens in your balance, whatever. How would you write a circuit that verifies the minimum amount without showing?
Yeah, so the question is like, can you make ZK proofs, and this is veering a little bit away from Battleship territory, but can you make ZK proofs that prove that you owned a certain amount of tokens at such and such time? The answer is yes, but it is very difficult. We have some prototype circuits for this. To put in context sort of the size of those circuits, the circuit that we just built today has about 1,300 constraints, which is the primary measure in this current proving system of circuit complexity. In order to prove that you know a private key corresponding to a specific Ethereum address. First of all, that is going to take about 100,000 constraints. And then furthermore, to prove that, like, at least with our current best known implementations, that a storage slot contains a certain value at a certain block header, I think we're at like 20 million constraints or something for that right now. There's a lot of optimization vectors still, but this is definitely like an ongoing field of work with a lot to do. So yeah, I encourage people to check out ZK programming. Question? The question is, will this get any better after the merge? The answer is, yeah, there's a couple things that are going to make this better. The first is that Ethereum's like state trie encoding is switching to something much more sane, from like the Hexary Merkle Patricia trie to like SSZ. So I think that's going to make things better. And then other things that are going to improve are that we're actually going to be moving onto new proving systems that make it easier to make certain kinds of mathematical claims that are very expensive right now. All right, so to wrap things up, what we did today was we put together a simple circuit for Battleship, and we hooked it up into an app that allows you to generate and verify proofs end to end. So you can construct your own little sort of like manual Battleship game out of this using only cryptography. I just sort of want to emphasize like how like exciting this is. What we did today was, you know, in comparison to like, let's say like 20 years ago, if you wanted to, you know, build out some sort of language for making a particular type of claim with a particular type of privacy, you only had special purpose tools at your disposal. You'd have to go to a cryptographer and ask them like, hey, can you invent some new math for me to, you know, allow me to prove that I know a private key corresponding to like one of these n public keys in a set and like subject to these other conditions. And they would invent some new math, and then you would, you know, basically like implement that new math and then have this whole new protocol. What we have now is we have a programming language for cryptography in some sense. We've basically been able to encode arbitrary game rules inside of a ZK snark. And this is one of the reasons why at Xerox PARC we're so excited about this stuff. And I know some folks might be coming to our ZK workshops on Saturday and Sunday. If you're curious to learn more, we have a lot of resources online again. But yeah, thanks everyone for coming.